Okay, hello everyone, this is Carter. In this video, I'm going to be reviewing particle motion. So let's remember that all the motion that we are looking at right now is in one dimension. So in the first semester of Calculus BC and in all of Calculus AB, we're going to be looking at motion in one dimension. And this can be seen as kind of just like a number line that we've seen a lot in our math experience. So the three main terms that we're going to be looking at when we talk about particle motion are position, velocity, and acceleration. So position is defined as where the particle is at a moment in time. And the first derivative of position is velocity, and that is the rate at which the particle's position changes with respect to time. And then the second derivative of position and the first derivative of velocity is acceleration, and that is the rate at which the particle's velocity changes with respect to time. And in these FRQs dealing with particle motion, position will commonly be written as x of t, where t is time and x is meters. Velocity will be commonly written as v of t, x prime of t, dx dt, and that is measured in meters per second. Acceleration, commonly written as a lot of things, a of t, v prime of t, x double prime of t, dv dt, and that is measured in meters per second per second. Okay, so let's describe particle motion in one dimension. And as we can see here, we're describing it using this number line here because it's just one dimension. So let's say a particle travels to the right over a certain period of time. As we can see here, we have this initial position, x0, and this final position, x1. And it is moving to the right over this time period. So is the particle's velocity going to be positive or negative? So let's think about what's happening to position here. Because as we remember, we define velocity as the rate at which the particle's position changes with respect to time. So how is this particle's position changing? Well, it's moving to the right, which basically means that its position is increasing. So since its position is increasing, we know that its velocity must be positive because we know from our calculus experience that if a function is increasing, then its first derivative will be positive. And since velocity is the first derivative of position, when position is increasing, velocity will be positive. So here, when the particle is moving to the right over this time period, meaning that its position is increasing, velocity must be positive. So we can make this statement here that since the first derivative of a function is positive when the function is increasing, we know that because of that, we know that when a particle's position is increasing, its velocity will be positive. And similarly, we also know that when the particle's position is decreasing, its velocity will be negative. So looking at the same kind of number line example that we were looking at a minute ago, we know that a particle is moving to the right when the velocity is positive. And this kind of question that is like, is the particle moving to the right or to the left? Or when is the particle, what time periods is the particle moving to the right? We will commonly see that on these particle motion free responses. So this is very important to understand that a particle moving to the right is the same thing as saying its position is increasing. So thus, its velocity will be positive. And the same thing here. A particle is moving to the left when velocity is negative. When the particle's position is decreasing, its velocity will be negative. And we also know that when a particle is at rest, its velocity will be zero. And this makes sense because when a particle is at rest, its position is not changing, so its velocity must be zero. Now let's look at speed. So speed is the rate at which a particle's position changes with respect to time regardless of direction. That's the technical term of speed. And when it says regardless of direction, that means that it doesn't matter if the particle is moving to the left or to the right. Speed will always be positive. Think about it like if you're a car. It doesn't matter if you're driving your car, if it's reversing, going forward, no matter what, speed will always show up as positive. And that is why we write speed as the absolute value of velocity. And just like velocity, it is measured in meters per second. So let's think about the translation of the velocity graph and the speed graph. It's very similar to the y equals x graph and the y equals absolute value of x graph. Obviously, because velocity is just v, and speed is the absolute value of velocity. So as we can see here in this scenario where velocity is decreasing, speed will also decrease, but then when velocity becomes negative, speed will not become negative, it will remain positive. So if we're thinking about this, if we're saying when velocity becomes negative, that's when you're reversing in your car. Speed is saying, oh, it doesn't matter if I'm reversing in my car. Speed will always be positive. So the faster I'm reversing in my car, if you're looking at it from velocity, the faster you're reversing in your car, the more negative velocity will be. But with speed, the faster you're reversing in your car, the more positive speed will be. So we can think about it right here, is right when we're starting to reverse. And when we're continuing to reverse faster, our velocity is getting more negative. And when we're looking at the speed graph, this is right where we're starting to reverse. We're not moving very quickly, but when we begin to reverse more, our speed is increasing. And that's similar to the y equals x and y equals absolute value of x, where the absolute value of x will never be negative. Okay, so now let's think about the important kind of question. Is a particle speeding up or slowing down? And just like when you're asking if a particle is moving to the left or right, this question is commonly on these particle motion FRQs. So a particle is speeding up when speed is increasing, or when the absolute value of velocity is increasing. So if we look at this graph here, this red arrow and this blue arrow both represent instances where speed is increasing, where absolute value of velocity is increasing, because the absolute value is increasing when velocity is getting further away from this x-axis. That means that the absolute value is increasing. So that is why these two arrows would represent when speed is increasing. So let's think about these arrows. The red arrow has an increasing speed, and its velocity and acceleration are both positive because its velocity is above the x-axis, so it's positive, and its acceleration is positive because its velocity is increasing, which is represented by this arrow. The blue arrow has an increasing speed, and its velocity and acceleration are both negative because its velocity is under the x-axis, so it is certainly negative, and its acceleration is negative because its velocity is continuing to decrease. Now let's think about when a particle is slowing down. That happens when speed is decreasing, as we can represent on this velocity graph with these two arrows that are pointed towards the x-axis. Since they're pointed towards the x-axis, that means that the absolute value of velocity is decreasing. So let's think about these two arrows. The blue arrow has a decreasing speed, and its velocity is positive because it's above the x-axis, and its acceleration is negative because its velocity is decreasing. And the red arrow has a decreasing speed, and its velocity is negative because it's below the x-axis, while its acceleration is positive because its velocity is increasing. So the conclusion that we can come to here, and this is very important, this is a very important concept that you really need to know for these FRQs. A particle is speeding up when its velocity and acceleration have the same sign. So if they're both positive, that means that it's speeding up, or if they're both negative, that means that it's speeding up. And a particle is slowing down when its velocity and acceleration have opposite signs. So if velocity is positive and acceleration is negative, it's slowing down. And if velocity is negative and acceleration is positive, then it is also slowing down. So let's kind of think about this. So with this red arrow, it has a positive velocity and acceleration, and that is why it is speeding up, because they're the same sign. And this blue arrow here, it is also speeding up, and velocity and acceleration are both negative, so they both have the same sign. So that is why it is speeding up. And it's slowing down. It slows down when a particle slows down when velocity and acceleration have opposite signs. So with the blue arrow, velocity is positive and acceleration is negative, opposite signs. And with the red arrow, velocity is negative and acceleration is positive, opposite signs. So let's think about this in the real world. So an example of positive velocity and positive acceleration is, let's think about that with our car. That is really just like when you're at a red light and then it turns green, so you begin to drive forward. So that can be thought of as your car speeding up. Obviously, when you're at rest at a stoplight and then you begin to go forward, you are speeding up because you have positive velocity and positive acceleration. And then what about when we have negative velocity and negative acceleration? That is like a car reversing out of its garage from rest. So you're starting out at rest, and then you're reversing, which represents a negative velocity, and your velocity is decreasing, so you have a negative acceleration. So that is also speeding up. Now let's think about an example where you have a positive velocity and a negative acceleration. That is like your car braking when there is a stop sign because you're still going forward, so your velocity is positive, but your velocity is beginning to decrease, so you have a negative acceleration. And obviously, when you're braking, when you get to a stop sign, you are slowing down. And then a negative velocity and a positive acceleration. This is all an awkward moment we experience. We're pulling out of a parking spot, and then as we're pulling out, we see a car that is driving past us. And we're like, oh no, we're about to hit that car. So we brake really quickly so they don't run into the back of our car. And we can think of that as slowing down as well because you are braking, and it is a negative velocity because you are reversing, but it's a positive acceleration because you are reversing less as you brake. So those are all examples in the real world of where you are speeding up or slowing down. And as we can see, this kind of proves that when you have a velocity and acceleration with the same sign, you will speed up. And when you have a velocity and acceleration with opposite signs, you will slow down. Okay, so now let's go over distance and displacement. And I covered this extensively in my last two videos. So if you really want an extensive explanation of these concepts, you should go watch those. So as we learned, displacement is simply the particle's change in position, which can be written as x final minus x initial. And this basically means how far the particle is from where it started. And then we have total distance traveled, and that is the particle's change in distance over a certain period of time, also known as how much distance has the particle covered. So let's think of a really simple example here. These concepts are really not that hard to understand, just really conceptually. The really hard thing that students, I would assume, trip up with is forgetting how to use integrals to calculate them. So you really just need to memorize those formulas, but it's nice to really have an understanding of what these things mean. So the simple example is I walk 10 meters to the right and then I walk 5 meters to the left. So I'm walking 10 meters to the left. My initial position is x0. I walk 10 meters to the right. I'm at x1. And then I walk 5 meters to the left. I'm at x2. So my displacement is how far particle is from where it started. So what is the distance between x0 and x2? That's how far away I am from where I started, because I started at x0, I ended at x2. And I'm simply 5 meters away because I am 5 meters away from where I started. Now let's think about total distance traveled. So we traveled 10 meters to the right, we traveled 5 meters to the left, so our total distance traveled is simply 15 meters. It's like the odometer on our car. It's just adding the distances that we go. So now let's think about distance and displacement in relation to the fundamental theorem of calculus, which I was really talking a lot about in my last two videos. So as we know, the fundamental theorem of calculus says that the integral of lowercase f of x from a to b dx, that equals capital F of b minus capital F of a, where lowercase f is the derivative of capital F. So basically what we're doing here is we are using the derivative of a function, because lowercase f is the derivative of uppercase f. We're using that derivative to calculate the change of that function. We are using this lowercase f to calculate the change of f, because we are taking the integral of lowercase f from a to b, and by doing that we can calculate the change in the uppercase f from a to b. And then we have displacement. And this looks really similar because we define displacement as the change from x initial to x final. So x final minus x initial equals displacement. And we know that displacement is the integral of velocity from time 0 to time 1, or time final. So this kind of formula that we set, this equation that we set up here, looks very similar to the fundamental theorem of calculus, because we know that velocity is the derivative of position. So we are using the derivative of position, which is velocity, to calculate the change in position, which is displacement. So that's why displacement equals the integral of velocity from time initial to time final. And then we can also calculate total distance traveled using an integral. So the integral of speed, or absolute value of velocity from time initial to time final, this equals the change in distance, which I wrote with this capital D. It is d final minus d initial. So we are using the derivative of distance, which is speed, to calculate the change in distance, which is total distance traveled, the change in distance. So, and if you want more explanation on this, I suggest you go watch my last two videos. But that's all I'm going to talk about with that. But really the main thing you need to know is these two formulas, because it's going to ask the particle's displacement a lot. It's going to give you the velocity, and it might ask the displacement or the total distance traveled, and you're usually just going to be plugging this into your calculator. Okay, so now let's talk about how to find the average velocity, acceleration, or speed of a particle. This is also a very common FRQ question. So we all know how to take an average of, like a set of data. You're adding up all the sets of data, and then you're dividing by the amount of sets of data. So like if, we have three numbers, 7, 2, and 3, those add up to 12, and we divide by 3 because there's three numbers, the average is 4. That is exactly what we are doing here with average velocity. We are adding up all these velocities by taking an integral from time initial to time final, and then we are essentially dividing it, or it's written as multiplying it, by 1 over time final minus time initial. We are essentially just adding up all these velocities in a certain time period and then dividing it by the amount of time that has gone by. Really what we do when we find the average of anything. But what we are really doing is we are dividing the particle's displacement, because the integral of velocity from time initial to time final is its displacement. We're dividing that by the amount of time since time initial. That's really what we are doing. And we can also find the average velocity by using position. So if we're looking at an FRQ and it's going to ask us for the average velocity, we can either find that by using the particle's velocity or its position, which will commonly show up as a graph. So if we're trying to find the average velocity using position, we can find average velocity by calculating the slope of the secant line between x initial and x final. So let's think about this position graph. So we are traveling 3 meters in 5 seconds, but we're not traveling in a straight line. We're going like 3 meters, and then we're going back a meter, and then we're going forward a meter, and then we're going back a meter. But we're ending up 3 meters away from where we started, and it took us 5 seconds. So in some cases here, we had a positive velocity. In some cases here, we had a negative velocity, like right here. We had a positive velocity again, and then we had a negative velocity. So we're really just adding up all these velocities to find the average velocity. But we can do that by just taking the slope of this line, and it's a secant line because this is x final, and this line at the axis is x initial. So really, we're making a secant line by connecting these points and then finding the slope of that line. So the slope of the line here is just 3/5 meters per second. So the average velocity is just 3/5 meters per second. So that's the second way that we can find average velocity. And then how do we find the average speed of a particle? This is really easy conceptually. So if I just say, let's say I drive 180 miles in 6 hours. What is my average speed in miles per hour? Well, we know how many miles we drove, and we know how long it took us, so we just divide. We do 180 divided by 6, so our average speed is just 30 miles per hour. This is really simple. And you guys probably thought about this when you were growing up going on road trips, because realistically, you're not going at a constant speed the whole time. When you're going on a road trip, you might be driving 40 miles an hour, you might be driving 70 miles an hour. It really doesn't matter, but you can find this average speed. This is how you find it. You can just find it by dividing the total distance you went by the time it took. So that's essentially what we're doing. But how do we find the total distance that we traveled? Oh, we do it using this integral of speed from initial time to end time. And then we divide this by the time it took, time final minus time initial. So essentially, average speed is just the average speed is just the integral from initial time to final time of speed dt divided by the time it took, which is exactly what we're doing here. We're just adding up the total distance we drove by the time it took. And lastly, we're going to talk about average acceleration. And it's very similar to how we find average velocity. What we can do is, just like any average we take, we are adding up all the numbers and then dividing by the amount of numbers. So we are using an integral from initial time to end time to add up all these accelerations, and then we are dividing it by the amount of time it took. Or here we are multiplying it by 1 divided by time final minus time initial, which is essentially just dividing it, But we can also, just like with velocity, we can find the slope of the secant line of velocity from initial velocity to final velocity, and that can also find us the average acceleration. And you already saw me do that with that other graph, but we can find this slope here, and that slope will be the average acceleration. So thank you guys. That is all I have to say about particle motion, but yeah, thank you.